And I'll just talk about Aaron's homework. Okay, so Ryan and I, you didn't do it, I believe. Just focus your stuff. Focus on calculus, okay? And Lily hasn't done her stuff, so I'll just cover Aaron's homework. Okay, so Aaron, you have three questions, three wrong questions, but two of them are almost correct. I'll just cover that, and then only one question I believe I need to explain it. Okay. So one is 8.25, Aaron. This question you got it right. It's just that you have to convert it back to decimal number. Okay, because the question says, okay, which question was that? 825. So 825, um, it wanted you to find the smallest integer, that whatever. Okay. So after you find a number, you want to um, transform it back to a decimal representation. Okay, that's just it. And I believe you know how, right? So just this one. And 8.28, I will talk about it later. And then 832. So 832, you were considering the choices for each digit, right? So that was correct. It's just that even the first digit could be a zero because the question didn't say it's a binary digit. So if you read the question said it's an 8-bit binary word. So if it is a binary word but not a binary number, then that means you can start with zero. Something like say um, the car plate, the plate number for your car, you can start with zero. You could have 0, 8, 2, whatever, right? So you can start with zero for a car plate number, the plate number of a car. Okay, yeah. So it's just a bit of a wording problem. Okay, so if you understand it as a binary digit and it couldn't start with a one or zero, it doesn't matter because the way you consider the question was correct. Okay, so the only question I need to talk about here is 828. And Aaron, later we can see if you have any difficulty solving the harder questions, then we can talk about them, and then we can move on to the next chapter. Okay? So 828. Okay. Determine the largest possible integer n such that this number is divisible by 15 to the power of n. So Aaron did this question by dividing by 15. So let's see Aaron's work. Okay, so Aaron divided by 15 and divided by 15 again, right? That is something we learn in our class, right? We divide by say divided by 15 and divided by 15 squared and stuff, right? But Aaron, notice that here 15 is not a prime number, right? 15 is not prime. 15 is 3 times 5. So when we have a big factorial, if we want it to be divided by a lot of 15s, then that means we just want it to be divisible by a bunch of 3s and a bunch of 5s, right? And notice that in a factorial, the number of 5s is always more than the number of 3s, correct? And so when you have 3, you have a 3. When you have 5 factorial, you have a 3 and a 5. When you have 6 factorial, you have 2 3s and 1 5, right? Something like say 10 factorial, you have 2 5s, but you have 3 3s, actually 4 3s, because there's a 9. Okay, so the number of 5s, so the number of 3s always outnumber the number of 5s, right? So basically here, we just need to consider the number of 5s in 942 factorial. So instead of divided by 15, we should divide it by 5 and then 25 and then 125 and stuff. Does that make sense, Aaron? Yeah. Okay, so right now makes sense. You only need to consider number 5. So this is the same as when we considered case like remember in example problems we did we considered how many zeros, how many trading zeros are there, at the end of a factorial, right? When we considered trading zeros, we were considering how many tens there were. And when we consider tens, tens are 2 times 5, and the number 5 always outnumbered the number 2s, right? So you only need to consider the number 5s, not merely just divided by 10, okay? Because if you just divide it by 15, you're simply considering, factors such as 15, 30, 45, 60, only multiples of 15, right? But every 3 and 5 can give you 15. Say 3 times 5, say 6 times 10, say, 9 times 15. Okay, any number, 3 and 5 can give you 15, not only just multiples of 15. You have to make sure it's a prime number. Okay, I hope I explained enough. Make sense? Yeah, so just consider number 5s. So just divide by 5. So that is, I think you should know how. You just divide by 5, get an answer, and then divide by 5 again, get an answer, take the integer, right, and stuff. Okay, so grab a calculator. So the first one is 942 divided by 5. That's 188, 2 and 5. And then you do 188 divided by 5, right? And that is 37, 3, and 3 over 5. And just keep doing this. And then eventually add all the integers up. Any question at all? Okay, good. And let's move on. So Aaron, I believe you did every problem before 833, right? So starting from 833, we can do a few problems together before we move on to the next chapter. Okay. On this page, from 833 to 838, do you have any questions you want to have a look with me and with us? And also Lily. So Lily, I haven't got any homework from you in challenge part. So see if you have any questions that you
I
want
was
to
just
go.
stuck on, yeah, sorry. I was just stuck on 8.34 and 35.
You got stuck on 34 and 35? Okay. So stuck on 34, yeah. Stuck on 34 and 35. Okay, and then we can talk about 34 and 35. Okay. So let's see. How many positive integers requires 3 digits when written in base 12, but require 4 digits when written in base 8? So maybe you can get an inequality here, right? So an integer, you could suppose it to be any number, let's just suppose it to be n, right? So this integer, it requires 3 digits when written in base 12. How do we set up, say, an inequality here? Any idea? So this part, right? 3 digits when written in base 12. So we could say this number is less than what? If it requires 3 digits, not 4 digits, not 2 digits, right?
Is it it's less than BBB?
Yeah,
So,
or yeah, exactly, right? Less than or equal to if you use BBB base 12, right? Very nice. Very nice. Okay. Or in other words, you could say 1000 in base 12 if you use smaller than. Yeah, make sense? So you could say it is smaller than only 3 digits. So it's definitely smaller than 1000, 1000 in base 12. If it is less than that, that means we have 3 digits for it, right? 3 digits in base 12. Or you could write down it is less than or equal to and use BBB 12, right? And of course, it's greater than, but greater than doesn't really matter because you have another condition here, right? But for greater than, let's just write it down 2 digits. So it's greater than BB 12, or if you want to use equal to, then that's the smallest 3 digit in base 12, which is 100 in base 12. Okay, that's what the first condition translates into. Yeah. Okay, good. So what about the second condition? 4 digits when written in base 8. 4 digits written in base 8.
Like bigger than 99? No, 73 7.
Yeah, 37777, right? So
Yeah.
bigger than the larger 3 digit in base 10 in base 8. So that would be 777 in base 8. Or in other words, you can also write down greater than or equal to the smallest 4 digit base 8, right? Very good. So Aaron, does that make sense? And for the less than part, it's not really that important because obviously it will be restricted by that, right? But still, let's just write it down. It's less than the smallest 5 digit in base 8, which is 10000, and then in base 8. Or you could say it's less than or equal to the largest the largest 4 digit in base 8, which is 7777 in base 8. Okay, whatever, right? As long as we understand it's going to be this and then this or this, okay? So which one is the easiest to work on? Among all these numbers, I believe these numbers are the easiest to work on, right? If you have 1 and followed by a bunch of zeros, you're just going to do, for example, this one is just 12 to the power 4. Yeah? And this one is 8 to the power 4. Okay, so we would...
to the power of 3?
No, 12 to 3, yeah. Sorry. 12 to the power of 3, 12 cubed, and 8 cubed, yes. Okay? Yeah, my bad. Very good. So these ones are the easiest to work on. Then we choose this, and we choose this. So that means it's just going to be less than 12 cubed and more than or equal to 8 cubed. So yeah, that's the answer. Then we're just gonna look for their specific values. This is 152, 112 less than or equal to n, and less than 12 cubed, that is 1728. So eventually that means n could be any number between 5, 12, 5, 13, and all the way to 1727, right? And that means we have 1727 minus 152, 512 plus 1, add 1 back, right? And that is 1216. Oh, this many numbers. Okay. Is there any more question about this, Aaron? Okay, really? Make sense? So yeah, smaller than the smallest 4 digit in base 12, and bigger than the smallest 4 digit in base 8. That's it. Okay, hope that makes sense. And then let's move on to the next problem. So 35 you were also stuck on? Okay. So find the 100 smallest positive integer that can be written using only the digits 1, 3, 5 in base 7. Okay, so let's see if you have any idea of how to do this. Shoot. Okay, so is there any idea? So Aaron, when you thought about it, did you?
Yeah, I listed the numbers. So like 1 base 7, 2 base 7, 3 base 7, 4 base 7, 5 base 7, 6 base 7, and then 10 base 7, and then crossing out all the even numbers.
Even
So
numbers,
yeah,
leaving 1, 3, 5 out.
yes.
Yeah, but yeah, that would work. Except that you have to make the list really long, right?
Yeah, so if every so like if we have 100 numbers, then we would be crossing out, because that was the point I was stuck on, because I didn't know how many had to be canceled in order to get the other part of the set.
Yeah. I think it's pretty hard to figure out how many numbers will be canceled out, will be crossed off, right? But how about without crossing off those even numbers? What about we just write down the numbers that only only use digits 1, 3, 5, and see if that works, right? We only use
Yeah.
1, 3, 5 to write down some numbers in base 7 and see if it works. See if it gives us any revelations. See if it can help. Okay. So for one digit, like a single digit in base 7, you only have 1, 3, 5, right? So you write down 1, 3, 5. There were only three one-digit number in base 7 that uses 1, 3, 5, right? Only three. Okay. So only three numbers, three one-digit numbers. Okay. Maybe I'm gonna write out this. So this is for one digit. Okay. How about two-digit numbers? How many two-digit numbers are there in base 7 that can be written only using digits 1, 3, 5? So that's not hard. When you think about it, there were two digits, so there were two spaces or two choices, right? The first number could be either 1, 3, 5, and the second digit could also be either 1, 3, 5, right? So in other words, you have 1, 1, 1, 3, 1, 5, 3, 1, 3, 3, 3, 5, and then 5, 1, 5, 3, 5, 5. So in other words, you have three choices for each digit, and that means you have 3 times 3, 9 digits here. Does that make sense? Right? So to think about this simply, you can just think about there were two spaces in base 7. The first digit could be one of the digit here, 1, 3, 5. The second digit can also be one of the digits, one of 1, 3, 5 here, one of 1, 3, 5. So that means we have 3 times 3, 3 squared, 9 choices, 9 possible numbers here. Yeah, so specifically there were 1, 1, 1, 3, 1, 5, 3, 1, 3, 3, 3, 5, 5, 1, 5, 3, 5, 5, and everything base 7. Does that make sense? So there were 9 possible numbers, possible 2-digit numbers in base 7 using 135. So that means, say that you need to write down the 12th smallest number, then it's just going to be this. We have already found the first 12 smallest numbers in base 7 that only use 135. Does that make sense? Yeah, then we just keep doing this, right? So for 3-digit numbers in base 7, how many numbers do you think there are?
27.
27, good, yes. Same stuff, right? So 3 cubed, 27. And this is not enough, right? So now we have 3 and 9 and 27. How many are there? That's 39, right? So now we've already had 39 numbers, not enough. We have to move on to a 4-digit. So how many 4-digit numbers are there?
3 to the power of 4 and 81.
81. Good. Has it exceeded 100? I think so, right?
Yes.
So if we add all of these up, we have 3 plus 9 plus 27 plus 81, and that's 39, 81. That's 120. So that means if we do 5555, so the last number 55, the biggest 4-digit number here, that is actually the 120th number. Make sense? Now we have to go back a little bit to find the 100th number. So how can we do that? Any idea?
Go 20 numbers backwards.
Yeah, we have to count 20 numbers backwards. Is there any way to, so maybe you were thinking we can do 5553, 5551, and just go back one by one. Is there a faster way? Think about this. I'm gonna give you a hint. Now, what if we do say 5155 compared to 15555? Where is 15155? So how many numbers are there between these two numbers? Or which position is this number?
We have to subtract. Do we?
Think about the numbers between them, okay? For example, let's say this is 5155 between this and 5555. So between both numbers, this number, if you increase it by 1 position, the next number, because both 55 are the biggest digit available here, right? You can only use 135. So the number bigger than that, you have to do 5, and I have to do 3, and I have to do 1, right? Does that make sense? This is number next to it, because 5 is the biggest number. If you want to find a bigger number, then that means you have to make this one a little bit big, and 2 isn't available, right? So you have to choose 3 for it, and then you can do 1 and stuff. Does that make sense? So the question is, if you start with 53, and the next number, of course, is 5313 and stuff, right? So if you start with 53, how many numbers are there? If you start with 53, then that means you only have 2 digits that are available to be chosen,
9.
right? 9, very good. And for each digit, for each space here, you have 3 choices. So that means there were 9 numbers here. Does that make sense? Yeah. So I'm gonna put this maybe down here. So this means that here we have 3 squared, right? 3 squared, 9 digits here. Okay. What about so after we run after say that we listed out all 9 digits here, then we have to go 55 something, right? We have to start with 55. Make sense? So that means after all of these, you're gonna start with a 5511 and also 5513. So what about all the numbers here? From 5511 all the way till 5555. How many digits are there? Same thing, right? Two available digits to be chosen. So still 3 squared, 9 digits here, right? Does that make sense? When we go back, since there were 20 numbers to go back, obviously you don't want to just go back one by one, right? If you go, I mean, when you go back one by one, it works. Only 20 numbers, you can still work it out. But still, compares to it can be a lengthy process. So try to figure out a way to go back by 3 numbers or by 9 numbers at one time, okay? Think about this. If you go back by 3 numbers at one time, that means you go back from 5 to 3 to 1. That just means that the second digit goes down by a unit. And in this case, when you go down, you cannot go down to 4, you can only go down to 3. Right? Make sense? Yeah. Okay. So turns out if you go down by 2 digits, from 5 to 3, and then this digit go back to 1, just 9 digits here, 9 digits here. Okay. So that means if this number is the 1/20th number, now you go back 9 numbers, you go back another 9 numbers, and that means which number is 5155? Now you have gone back 18 numbers, right? So that's the 102nd number. Does that make sense? Right? From the 1/20th number, you go back 3 and 9 numbers to go back to 5511, right? And then you go back another 9 numbers, you can go back to 5311. So in total, there were 18 numbers here, and that means 5155 is the 102nd number. Okay, and then to find the 100th number, just need to go back by 2 more, right? So 5151. 5155 is the 102nd, 51 and 53, that's the 101st, and then go back by another one, 5151, that's the 100th number. Does that make sense? This is the 102nd, this is the 101st, and you go back by another one, that's the 100th number. Okay. Here, if you start by 53 something, then that means you have the 103, from 103 to 100 minus 9, 111th number, right? So from 103 to 111th number, they start with 53. So from 5311 to 5355, okay? Matches onto 5311 all the way to 5355. And then from 112th number to 120th number, that would be 5511 and all the way to 5555. So that's how you go back by 20 numbers. Not one by one, because it might take too long time. And also, if you go back one by one, if you make any mistake during the process, you're gonna have a wrong answer, right? So when you go back, try to do this. Try to figure out how many choices do you have for the digits here. Like to use this kind of thinking over and over again, so that you don't make any mistake. Does that make sense? Yeah. Okay, good. Good. Lily, does that make sense? Do you have any question about this? Good. Okay. Nice. So after 835, let's see. So 36, 37, 38. Aaron, have you tried them for now?
No, I haven't tried any problems starting from 836.
Okay. I'm not sure. So Lily, do you have any question you want to talk about? Let's see maybe the last page. See if you guys, Lily or Aaron, if you guys want to talk about any question or maybe you want to prefer to try it first. If you want to try it first, then we can just try it first before we talk about it. And we can talk about chapter 9 first.
Are there number theory questions in AMC?
There were what? One question in AMC?
Yeah, oh, okay, never mind.
What do you mean? Oh, you meant is there any questions like in this chapter that will be on AMC? Well,
Yes.
definitely. Okay. Number theory will always appear in AMC 10. Yeah. So there's an AMC question. Maybe let's have a look at an AMC question. Okay. Maybe let's have a look at this and then we can move on to the next chapter. Yeah, you guys can take your time to read the question. This question, I remember was from AMC 10 in like just 3 or 5 years ago. In recent 3, 4, 5 years. Oh, not far one. Couldn't remember. But anyway, any idea? Basically, just counting from 1 to 2005. Oh, and that should be the 2005 one. Sorry. Yeah. So almost 20 years ago, actually. Yeah, right? It must be from the 2005 AMC. So 2005, from counting from 1 to 2005 without using digit 4, right? That's all it's asking. How many numbers are there?
So it's basically just digits 1 to 2005 excluding the digit 4.
Yeah. The digit 4 has always been skipped. Any idea, Lily, Aaron? Right? No? Okay. So if there's no idea, I believe from the last question, if I give you a little bit hint, it could help with this question, okay? So let's go back to last question and see if there's any other way to look at it, okay? The last question, I believe there was one very interesting pattern. Notice that in the last question, since we can only use digits 1, 3, 5, we can basically see this question as there were only 3 digits, right? So, okay, I mean, digits are merely just symbols, right? When we talk about 1, 2, 3, 4, 5, these are just some random symbols we invented as human beings, correct? So if you can only use 1, 3, 5, is there any difference from 1, 3, 5 to 0, 1, 2? If you use different symbol, if you only consider just the number of symbols, they're the same, right? Consider the number of symbols rather than the symbol itself. Okay, the symbol could appear as anything. The symbol could appear as star, a square, and a triangle. Say that in our world, we only have these 3 digits, and we count using these 3 digits. Then we start from star, and then we go to a square, and then we go to a triangle, and we do right? A square star, a square square, a square triangle, then triangle star, triangle square, triangle triangle, right? So the symbol itself, how the symbol appears doesn't really affect our way of counting, right? So all these numbers, they can appear whatever they want. They can appear as ABC, remember? Then you would just do A, B, C, and A is supposed to be 0, right? Then you do BA, BB, BC, CA, CB, CC. And then you do BAA, BAB, BAC, etc., etc. Does that make sense? Okay, so you only need to consider the number of symbols. Now, in this question, you only have 3 digits available, which are 1, 3, 5. So you can consider them to as 0, 1, 2. In other words, if you only have 0, 1, 2, okay. If you only have 0, 1, 2, then that, okay. So if you only have 0, 1, 2, you should have the following numbers. So 0 and 1 and 2, and then 1, 0, and then 1, 1, and 1, 2, and 2, 0, and 2, 1, and 2, 2, right? That's basically in base 3. This is base 3. If you have 1, 3, 5, then your numbers are 1, 3, 5, and then 1, 1, and then 1, 3, and then 1, 5, and then 3, 1, 3, 3, 3, 5, and then 5, 1, 5, 3, 5, 5, right? It's just that you can start with 1. Okay, so it's sort of like a base 3 number system because there were only 3 digits available. So it's sort of like a base 3. It's just that you can start with the first number because the first number isn't 0. Okay, that makes sense? So in this question, if you consider 1, 3, 5 as a 3-digit sort of system, that's how we realized that there were only 3 numbers in 1-digit representation, and there were 3 squared, 9 numbers in 2-digit representation and stuff, right? And then 3 cubed. Okay, try to think in this way. So in this question, you are skipping digit 4, right? So that means all the digits that are available to you are just 0, 1, 2, 3, no 4, and then 5, and then 6, and then 7, and then 8, and then 9, correct? So that means how many digits do you have available for you? You don't have 10 digits. You have to skip 4. That means you only have 9 digits, right? For available for you, only 9 digits. Now think about this. What difference does it make from this situation to another situation that say 9 is not available? If 9 is not available, you have 0, 1, 2, 3, 4, 5, 6, 7, and 8, right? In this case, if you have to skip 9, you also only have 9 digits available. But what is this? If you only have 0 to 8, isn't this just the base 9 system? Right? Does that make sense? If you're always skipping 9, that's basically just counting in a base 9 system, right? So here, if you're skipping 4, does it make any difference with this situation? No, right? Because still, you only have 9 symbols. Don't consider how the symbols look like. In the end, you only have 9 symbols to count. Does that make sense? So you only have 9 digits to count. That's the same as the base 9 system. Does that make sense? So when you skip 9, and when you skip 4, or if you need to skip 5, or if you need to skip 7, all of these are just the same. They're all the same, okay? And that's how we solve this problem. So when the odometer reads 2005, it actually means, because you're skipping 1 digit, it actually means that it's counting in base 9. Okay, so the 2005 is actually just a 2005 in base 9. That's it, okay? And that will give you, so actually how many miles has the car traveled? And then that's actually just 2 times 9 cubed plus 5. And then 729, 1, 4, um 1 4 6 5 8 1 4 1 4 6. Okay. 1 4 5 8 1 4 5. 1 4 6 2. 9 cubed. 1 4 6 3. Yeah. Okay. But 1 4 6 3, we need to minus one more because we are skipping 4, right? Since we're skipping 4, there's no 2004, so there's one more being skipped. So it's actually 1 4 6 2. Okay, but remember that there's no 2004, so that means you have to minus one more, and 1 4 6 2. Because if you just consider base 9, you are skipping 2009, right? You're actually skipping 2009 if you're counting base 9. So that's why 2005 in base 9, there were 1,463 numbers, but actually there's no 2004, so you minus another one. Okay, makes sense? And that's how we get this. Okay. Yeah, so if you're skipping any digit, that's the same as baseline system. So another way to consider this question, you can also think about this. If you start from 1 in this question, 1 something something something, how many numbers are there? You can also do this sort of analysis, and you will see that you have 9 choices here, 9 choices here, 9 choices here in this question, right? For these 3 digits, you can always put any of these digits on. So that means you have 9 and 9, right? So that means you have 9 cubed for this, okay? And then if you start with 0, that means you only have 2-digit numbers, okay? And then that means you can also do this kind of analysis, okay? And then do 0, we start with the 1 here, you have 9 squared, something like this, right? And then you can do 0, 2, there's also 9 squared. So you will see that from 1 something, 200 something, all the way to 900 something, you actually have a lot of 9 squared. You have 9 squared. 8 9 squared actually, because from 1 to 9 you're skipping 4. There were only 8 digits, right? And you just keep doing this, and 2-digit numbers and 1-digit numbers, and in the end, after you add everything up, you will just get 2 times 9 cubed. Okay, so I don't recommend this kind of method because you have to count the number of numbers for 4-digit and then 3 digits and then 2-digit and then 1 digit. It takes too much time. Okay, so consider it as a baseline system, except that you are skipping 4 instead of 9. So there's only one number you need to skip. Okay, any question for this? Does that make sense? The same as base 9, and you are skipping 4, so you're skipping 2004. 2004. That's the only trick here. Okay, Lily, does that make sense? Yeah, just always consider the number of symbols that you can use when you count, okay? So if we're talking about AMC, this ASHME is also AMC. ASHME is a precursor of AMC. AMC had a reform in 2002. I remember 2002 or 2001. Okay, so before 2001, AMC was named ASHME. Okay, so ASHME is the same as AMC. Yeah, you guys might want to have a look. Okay. So maybe we can do one more AMC question every this. This is ASHME AMC. Let's see. Take your time, read the question, and see if you have any idea. Question, any idea? 3 digits in base 7, and when you express in base 9, digits are reversed. And find a middle digit in either representation of n. Notice the word, the word choice either. Okay, when they said either, that means there were two possible representation of n, right? And in both possible representation, the middle digit is the same, and it's asking for that middle digit. OK， 所以Ryan 注意一下这个英文的用法啊 ，either 就表示二者选一嘛。所以当他说到 either 的时候，你就知道肯定是有两个答案，其实两个答案的 middle digit 是一样的。Anyone? I don't think this one is a hard. It's very hard. Okay, because if you don't know what 3 digits are, you can always suppose. So, what can you suppose it to be? 3 digits in base 7. Anyone? So Ryan, you have any idea?
Wait, just give me a second.
Sure. What can we suppose n to be? Three digits in base 7. Lily, any idea? 3 digits in base 7? What are these 3 digits? We can suppose them, right? How do we suppose them? Let them be what? Do you guys remember from the previous chapter, chapter 7? We said that we can use algebra to solve this kind of questions, right? When you have, say, a 3-digit number, what can you suppose it to be? Say a 3-digit number or 4-digit number or 2-digit number. What did we learn?
So when we had a 2-digit number, it was 10a plus b, but then in base 7, it would be multiplied by 7, like each digit.
Exactly, right? Yes, yes. So the digit, we can suppose it to be A and B. A 2-digit number, we're supposed to be AB. A 3-digit number, we can suppose to be ABC. That kind of stuff, right? Make sense? Really? That right? Okay. And then in base 10, we were saying, we can do 100 times A, 10 times B plus C, right? And then base 7, we just do 7 squared, 7 and 7 and then 1, right? And 7 to about 0. Okay, very good. So for 3 digits, we can suppose them to be ABC. And it's in base 7. So we could say N is ABC in base 7. Does that make sense? And to stress that this is a number, we put an underline here. Remember? Okay. This is from chapter 7, right? To remind you, so you guys remember, let's see. Let's start from, yeah, we're doing chapter like this, remember? 3 unique 2-digit numbers, we use this, right? A, B, C, D, E, F, this kind of thing. And also this, the 2-digit number, you're supposed to be A, B. It's just that in chapter 7, we're always dealing with number base 10. They use number base 10, so 10 to the power 1, 10 to the power 2, and stuff, right? And here, we're dealing with number base 7, then you use number base 7 rule, okay? So expressing in base 7, that's ABC. What about in base 9? Anyone? When the same number is expressed in base 9, the digits are reversed. So that means in base 9, what is the representation in base 9 here?
CBA.
BBA.
CBA, exactly. Reverse the digits. Very good. So CBA. So CBA in base 9. Okay, Lily, does that make sense to you? Okay, so if that makes sense, how can we transform these into an equation, algebra?
7 squared times A plus 7B plus 7.
7? ABC?
No. Plus 7 times 1. Wait,
Or
no.
C times 1, right?
C times 1.
C times 1. If C is 1, there's only 1 here. If C is 2, there were 2 here, right?
Yeah.
So C times 1, not 7 times 1.
Yeah.
And then equal to?
Equals to 9 squared times A plus 9B plus A.
9 squared times C, right?
Yeah, 9 squared times C.
Yeah, and plus 9B and plus A. Very good. Very good. Okay. So Lily, right now make sense? Okay, Lily, try make sure you understand this. Okay. So ABC in base 7, 7 squared times A, that's the 100th digit, right? And for B, that's 7B. For C, that's C times 1. C times 7 to the power 0. Okay. To be the most technical, you should write A times 7 squared, B times 7 to the power 1, C times 7 to the power 0. Guys, remember? That's basically what we learned in this chapter, right? Okay, so now we have this equation, we can simplify and try to solve it, right? Here we have 49A, 7B and C, and then we have 81C, 9B, and A. So we cancel out. We have 48A, maybe equals to 80C, and then plus 2B. Okay, let's keep every term positive and then simplify them, combine like terms, right? And here we can divide it by 2. So we get 24A, 40C plus a B. All right. Any idea further? So we simplify the equation. Now we gotta.
We need to know what B is.
Yeah, we need to know what B is.
So then that would mean that B is 24A minus 40C.
Okay, yeah. But yeah, and then we need to figure out the values of ABC, right?
Yes.
How do we figure out the values of ABC?
By substituting some numbers, substituting inside.
There's only one equation.
Oh, right.
Let me write down. B is 24A minus 40C, right?
Right.
Is there anything special about this? Anything we can observe from this expression?
It's factorable.
It's factorable. Very nice. And what can we factor to be?
8. 8 open bracket 3a minus 5c.
Very nice. What does it tell you
Um,
about
b is a multiple of 8.
Very good. B is a multiple of 8, right? So you could say 8 divides B, or if you don't remember that notation, B is a multiple of 8. And that gives you the answer. Why? B is a multiple of 8. So what can B be? Can B be 8? Is it possible
No.
for B to be 8?
Oh no,
Let's see.
it's not.
Yeah. It's in number base 7, right? So that means A, B, C, the biggest they can be is 6. Right? So A, B, C can only be the maximum of A, B, A or B or C is only 6 because they're the number base 7. So that means B has to be what number?
0.
0.
Yeah.
Very nice. 0. Okay. So A, B, C has to be less than 7. B could be 0 or 8, or of course 16 doesn't work, right? And negative numbers don't work. So, and B cannot be 8. So the only number B can be is 0. Okay, that makes sense. This is the easiest way to find out the value of B, because you don't have to work out the values of A or C. If you don't do this, then maybe you can try to just get some numbers, right? Try to put in some numbers and have a try. Okay, you can try that A is 1, I don't know, A is 2, C is 1, and then A is 3, C is 2, whatever. But keep trying it. You will see that eventually B can only be 0. Okay, but that takes too much of time. So here, if you factor it, you realize it's a multiple of A and it's less than 7, so it can only be 0. And by the way, if you want to find out which two numbers can satisfy this question, then we can start from here, right? If B is 0, that means 3A minus 5C is 0. And that's really easy to see what values they can be, right? Any idea? What can A and C be if you make this 0?
A is 5, C is 3.
Yeah, good. Any other possible?
They can both be
Number?
0.
Both being 0 because they're digits, right?
Oh, right,
So A
yeah.
and C,
So
yeah, couldn't be 0, the first digit. Yeah. So it seems like this is the only solution. Okay, and that it is the only solution, 5 and 3. So you go back. Basically, it means that 503 in base 7 is 305 in base 9. Okay, so these two numbers are the two numbers it meant, right? So either representation of n. Either representation, it means either in number base 7 representation or in number base 9 representation. There's only one answer actually. Okay, so either representation means that for this answer for the number n, the representation in base 7 and representation in base 9. In either representation, the middle digit is 0. So B is 0. Okay, so yeah, I think everyone understands. So Ryan, okay. Did any problem with this? No, okay with it? Okay. Try to redo this at home when you do your homework. Okay. Make sure you understand the process here. This is AMC. Okay, so there's one more. Okay, let's take a break, and after break, let's go over to chapter 9. Okay, so already 1 hour. So we come back at 8:10. I'm 8:10. So for you, that's 5:10. Okay, come back at 5:10, and then we continue to chapter 9. Okay, good. So chapter 9 is just arithmetic in base numbers. So arithmetic means addition, subtraction, multiplication, and division. Okay, just to the four basic arithmetics in different base number system. We've actually covered this in the very first class in when we talk about base numbers, if you guys remember, right? I was explaining how we how we can do addition, subtraction stuff, but today we review it, so it shouldn't be too hard. And yeah, and that's just that's the entire entirety of chapter 9. So let's look at some examples and try to weaken your memories about this. So let's say we add these two. In the first example, we're basically just adding these two numbers up. We have 21, 21 in base 6 plus 14 in base 6. When we actually studied this before, so there were the ways we studied was just to list down just as the way we learned addition when we were in elementary school, right? So we just do this 2 1 1 4. We do this. And 1 plus 4 is 5, let's remember, and 2 plus 1 is 3, and that's in base 6. There's no carryover, so that's it. 3 5 in base 6. Okay, that makes sense, everyone? Very easy stuff, okay? So alternatively, you can also use digit bundles to add them up, okay? You can also express them in base 10 and then add them up. So another way we do it is that 2 1 in 6 plus 1 4 in 6 we can do. So 2 1 is 2 times 6 to the power 1 plus 1 times 6 to the power 0. Right? That's what 2 1 in 6 means. And then for 1 4, 1 4 is 1 times 6 to the power 1 and then 4 times 6 to the power 0, correct? Okay, so you can add a digit bundles up. When you add them up, if you line them up nicely here, you will see it's very easy to add up. So here, if you add these two up, obviously you have 2 times 6 plus 1 times 6. So that gives you 3 times 6, right? And then you have 1 times 6 to the power 0, 4 times 6 to the power 0. That's obviously 5 times 6 to the power 0. So that's how you know that the result is 3 5 in base 6. Because this is literally 3 5 in base 6. Does that make sense? Okay, you will see that the method you learn with addition, subtraction, and multiplication and stuff literally just comes from adding or subtracting the digit bundles. This is the same as this, you see? It's just another way to write this down. So you can do a comparison here. Okay, the second digit here, 2 and 1, it simply means 2 times 1, 2 times 6, and 1 times 6. And this just means 1 times 1, 4 times 1. Okay, any question? Let me do next. So this is the same. I think 9.2 is very easy. I don't need to write it down. You just need to add them up, right? So 3 plus 2 equals 5, 3 plus 1 equals 4, 1 plus 3 equals 4. No carryover, 5, 4, 4. Okay, shouldn't be too hard. And then let's look at an example where we have carryover and we explain that using both logic, okay? Using both ways. So this one. This is 164 and 623. So 164, 623. We use digit, we can just add them up like this. And 4 plus 3 is 7. 6 plus 2 is 8. But that's base 8, right? In base 8, you don't have 8. When you have 8, you carry over, correct? So 6 plus 8 is 8. So you have to carry over. You get 0 and carry 1 over. And then 1 plus 6 is 7. 7 plus 1 is 8 again. So again, you have 8. So you're going to carry over and you'll get this. So that's 1007 in base 8. In other words, if you use digit bundles, you will see y. So to use digit bundles, 164 is going to be 1 times 8 squared plus 6 times 8 to the power of 1 plus 4 times 8 to the power of 0. Okay, and then plus 6 to 3, so 6 times 8 squared, 2 times 8 to the power of 1, and then 3 times 8 to the power of 0. Okay. Oh my God. Okay, and when we add this, you will see that. So first, the last digit is very easy. There's no carryover. 4 plus 3 is just 7, right? So the last one, you get 7 times 8 to the power of 0. And now notice here. Here is 6 times 8 plus 2 times 8. So you will get 8 times 8, correct? You should get 8 times 8 to the power of 1. But 8 times 8 to the power of 1, that's actually 8 squared. Okay, so that's why you're gonna carry over. This becomes 8 squared, so that's why it carry over to here. So for 8 above 1, here you actually only have 0, and then you have another 8 squared. So you could say we add another 8, 1 times 8 squared here. So that's why you carry over, that's why you carry over here. Okay, you are actually adding another 8 squared here. That's an 8. That's also why if you have, say, instead of a 6, if you have a 7 here, you will actually end up with 9 times 8 to the power of 1. And that means you're going to have an 8 squared and another 8 to the power of 1, right? So you're going to have a 1 here. This is going to be a 1. And you're going to have another 8 squared adding to the bunch of 8 squares. Okay, that makes sense, guys? That's why you carry over, okay? If that makes sense, the last one here, 1a squared, 6a squared, and another 1a squared. So in total, you would have 8a squared, right? So 8a squared. And again, that's going to be 8 cubed instead of any a squared, right? So this becomes, this carries over, this is gone. You actually have an 8 cubed. So that's why you also have 0a squared, and then you have 1 8 cubed. So that's how you add up the digit bundles. I think that makes sense. And in the end, 1 times 8 cubed, 0a squared, 0a to the power of 1, and 7a to the power of 0. That's just literally 1007 in base 8. Okay, any question? You add up digit bundles. It's the same as doing this. This is just a simplified version of adding these bundles. And the reason why you carry over is explained here.
So basically 1 0 here is 10 in base 8 is basically just one bundle.
Yeah, it's one bundle, which is 8.
Okay.
In this case. Yeah, very nice. Okay, so if that makes sense, we're gonna move on to subtraction. This is addition. So when we're doing subtraction, if we don't need to borrow, if you don't need to borrow from any digit, that's very easy. So the first one is 1, 2, and 2, 5. If you do a subtraction, that's just going to be 2, 5 in base 7 minus 1, 2 in base 7. And that's going to be 1, 3, right? 1, 3. And also you can use digit bundles to see that. Let's do an example here as a way to illustrate how everything is connected. So in this example, we're doing a subtraction. 537 in base 9 minus 216 in base 9. So first, you can always do this. 537, 216. There's no borrowing, very easy. 1, 2, 3. And every number is in base 9. Okay. And to understand this in digit bundles, you write them down, and just like addition, right? You should see it immediately. So this equals to 5 times 9 squared, 3 times 9 to the power of 1, 7 times 9 to the power 0, and do minus, right? Minus bracket, 2 times 9 squared, plus 1 times 9 to the power 1, plus 6 times 9 to the power 0. Okay, so do a subtraction, and everything's a subtraction. When you do this subtraction, you said every digit just matches, right? This is 7 times 9 to the power 0 minus 6 times 9 to the power 0, so you just get 1 times 9 to the power 0. And 3 times 9 minus 1 times 9, so that's why you get 2 times 9. And 5 times 9 squared minus 2 times 9 squared, that's why it gets 3 times 9 squared. So that's why you eventually just get 3 to 1 in the base 9. Okay, any question? Pretty simple, pretty straightforward, right? And then let's see an example if you when you need to borrow from a digit. That would be this. In this question, you have to borrow. So before we borrow it, we use digit bundle to see how we borrow it, okay? So again, this is in base 6. So 5 times 6 squared, 1 times 6, 4 times 6 to the power 0. And then minus, in this case, we're not going to use bracket. I'm just going to use a bunch of subtractions, okay? So minus 4 times 6 squared, minus 3 times 6 to the power 1, minus 3 times 6 to the power 0. And I'll do a subtraction. So go from the last digit, 4 minus 3, that's 1. That's very easy. We don't need to borrow from any digit. But look at this. Here, you have 1 minus 3. That's minus 2. This is actually minus 2 times 6, right? But if you just write down minus 2 times 6, that actually works, right? You can actually put it here. And here, 5 times 6 squared minus 4 times 6 squared is actually just 1 times 6 squared. This could work if you just need to find the result in base 10. But if you need to convert this to a base 6 integer, then that means you have to find a way to change this subtraction into an addition, correct? That makes sense, everyone, right? So if you just do a subtraction directly, you end up with this, but the problem is that there's a minus 2 here. And this minus 2 prevents you from writing this into a number in base 6. Okay, so we want to change it into a positive. That's what we meant by borrowing, okay? So we have to borrow a 6 squared from here. So 1 6 squared, if you borrow 1 6 squared, that means you only have 0 6 squared, right? So now you only have a 0 6 squared, and you give a 6 squared to 6 to the power 1, and that is actually 6 times 6 to the power 1. So you can understand this 1 times 6 squared as 0 times 6 squared plus 6 times 6 to the power 1. See if that makes sense? So this part comes from 1 times 6 squared, right? 1 times 6 squared, you use 1 times 6 squared so that you only have 0 6 squared, and then you have another 6 times 6 to the power 1. Okay, that's what we meant by borrowing, right? So you borrow 1 digit from here, that's why 1 goes down to 0, and you have 6 for 6 to the power 1 for this digit, for the second digit. Okay, so if it is actually a 3 here, you're gonna have a 2 here, and you borrow 1 6 squared from it, you're gonna have 1 6 squared and 6 times 6 to the power 1. You see? Okay, so if there are 2 here, you borrow 1, you have 1 left over. But you only have 1 here, so you only had 1 here, so when you borrow 1, you only have 0 times 6 squared. Okay, and everything else is the same. We copy it down to here. Okay, so basically 1 times 6 squared goes as this, and everything is the same. Now we can change it into a plus. So first is 0 times 6 squared. And now we can do this part, right? This part, 6 times 6, 2 times 6. So that's why you have 4 times 6. 4 times 6, and then 1 times 6 to the power 1, 6 to the power 0. So in the end, this is literally 4 1 in base 6. Okay, I think it should make sense. And compare all of these into with the stuff we learn in elementary school. That's 514 in base 6 minus 433 in base 6. So when we do this, 4 minus 3 is 1. That corresponds to, well, this part, right? 4 minus 3 is 1. And then 1 minus 3, that's not enough. When we said that when it's not enough, we're gonna borrow 1, right? So we mark here, we borrow 1 from that. And when we borrow a digit, this is in base 6. So we only borrow a 6 from it, not a 10. We're borrowing a 6 from it, right? When we were small, when we learned about this, we said we borrow a 10 from it because we were working in number base 10. But now you're working in number base 6, you're only borrowing a 6, okay? So make this a little bit smaller, okay. All right, so here, this borrowing gives you a 6 here. So 6 plus 1, that's 7, minus the 3, makes sense? 6 plus 1 minus 3, you're gonna have a 4. That's how you borrow it. And after you borrow it, this becomes a 4. 4 minus 4 is 0. So this is only 0 in base 6. So the answer is 4, 1 in base 6. And that's what happens here. You borrow 1, 1 becomes 0. And when you borrow 1, it's actually 6 times 6 to the power 1 minus 2 times 6 to the power 1. You have 4 times 6 to the power 1. It's a reverse of addition, right? Because in addition, if you exceed 6 times 6 to the power 1, you're gonna get a 6 squared. Remember? In example, before here, right? When you have 6 plus 2 times 8, which is 8 times 8, you're gonna change it to a squared. That's why you carry over, right? You get a squared, okay? When you exceed 8. In this case, when you when you borrow from 6 squared, you see it as 6 times 6 minus 2 times 6, and then you get 4 times 6. Okay, that's why you borrow. Does that make sense? Anyone has any more question about this? Okay, shouldn't be hard, right? Only subtraction and addition. And then let's move on to multiplication. So let's say we just do an example here. All right. So this is 3, 4 times 2, 4, 1 in base 6. Okay, I'm gonna illustrate this using digit bundles and also the way we learned in school, like this way. Okay, I'm not pretty sure what this is called in English, but yeah, or that way. Okay. So recall that previously when we discussed multiplication, we said that we have to set up a multiplication table, right? Because in base 6, the multiplication table doesn't work in the same way as we have in base 10. They're different, right? So we have to do some additions in base 6 to figure out a multiplication table for base 6. So let's try to do that. Now we have 2, 4, 1 in base 6 times 3, 4 in base 6. Okay, so the table isn't too hard. For 1 times anything, just anything, right? So you could say 1 times 1 is 1. I'm gonna skip that. Okay, so 1, 2, 3, 4, 5, right? 1 times 1 is 1. 1 times 2 is 2, right? 1 times 3 is 3. 1 times 4 is 4. 1 times 5 is 5. Okay, everything is in base 6. Okay, base 6 multiplication table. And let's work on 2 times 2. So 2 times 2. That's just 2 plus 2, right? And that is 4. And in base 6, we do have 4. So we just put 4 here. 2 times 3. Notice that we just need to add a 2 to 4. Okay. Now 2 plus 4 is 6, but it's in base 6. So that means you carry over, you get 1, 0. Okay, all the numbers here are in base 6. So it becomes 1, 0. Does that make sense to everyone? We construct a multiplication table, you just keep adding, right? So 2 times 4, you just add another 2, so it becomes 1, 2. And 2 times 5, you add another 2, that's going to be 1, 4. See, it's not hard, okay? Every time just add 2, right? Because multiplication in its essence is just addition. Okay, and then we move on. We move on to 3 times 3, right? Because 3 times 2 has been dealt with, okay? 3 times 3. So to figure out 3 times 3, you go from 2 times 3, right? 2 times 3 is 3 plus 3, that's 1, 0. And 3 times 3 is 3 plus 3 plus 3. So you just add another 3 to 1, 0. That makes sense, right? You add another 3, that's 1, 0 plus 3, so 1, 3. Okay, and then 3 times 4, you're going to add another 3, right? So 1, 3 plus another 3, that's 1, 6. And again, that's base 6, you carry over. So it becomes 2, 0. Right? And then 3 times 5, you add another 0, that's, another 3, that's going to be 2, 3. Okay, does everything make sense, Aaron, Lily? You add numbers, okay? And after 3 times 3, you're going to figure out 4 times 4, right? Because 4 times 3 has been dealt with. So 4 times 4, again, you work from here, right? So 4 plus a 4, that's 1, 2, plus a 4, that's 1, 6, which is 2, 0, right? And then plus a 4, 2, 0 plus a 4, that's 2, 4 in base 6. Eventually, you have 4 times 5, that's add another 4. So this is 2, 4 in base 6 plus a 4 in base 6. 4 plus 4 is 8, but every 6 you carry over, remember? So minus 6 is 2, and you carry over, that's going to be 3, 2. Okay, 2, 4 plus 4 is going to be 3, 2, right? You carry over. When you have a 6, you carry over. So it's going to be 3, 2 here. 3, 2 in base 6. And then eventually you have 5 times 5. That's the last one. So 5 times 5, again, compared to 3, 2, you add a 5, right? 5 plus a 5 is 1, 4, plus another 5, that's 2, 3. 2, 3 plus another 5, that's 3, 2. 3, 2 plus another 5, that's going to be 4, 1. Right? 3, 2 plus a 5. 7 minus 6 is 1, right? For 6 you carry over, that's 4, 1. And also you can observe a very nice pattern here. You see a pattern here? Consider the first number to be 0, 5. You see the pattern? 0, 5, 1, 4, 2, 3, 3, 2, 4, 1. It's in base 6. So you will see that the digit sum here is always 5. Right? 0, 5. And the tens digit goes up by 1. Units digit goes down by 1. 1, 4, 2, 3, 3, 2, 4, 1. Doesn't that remind you of anything of our multiplication table?
9. Multiplications of
9. Right? This is the multiplication of 9 in base 10. And you will see that the multiplication of 5 in base 6 has the same pattern. Right? 9, 18, 27, 36, remember, and 45, 5, 4, and reverse it. Yeah, so very nice pattern, okay? But anyway, this is the multiplication table for base 6. It's not that hard to construct one, right? You just keep adding. And you will see that this has the same feature as a multiplication table in base 10. See, it's like this way, remember? And 1, 1, 1, 2. Okay, now we have everything. We can do this multiplication. So first we do 1 times 4, right? 1 times 4 is 4, and then 4 times 4, right? What is 4 times 4? You check the multiplication table, that's 24. Okay, 2, 4. So 4 times 4 is 2, 4. You put a 4 here, you carry over 2. Right? And then you do 2 times 4. 2 times 4 is 1, 2. 1, 2 plus the 2, that becomes 1, 4. Does that make sense? Okay. And then you do 2, 4, 1 times 3, remember? To do multiplication. 2, 1, 4 times 3, right? So 1 times 3, you have a 3 here. And 4 times 3, so 4 times 3 is 3 times 4, it's going to be this, 2, 0, right? So 2 times 3 is 2, 0, carry over 2. And you do 2 times 3. 2 times 3 is this, 1, 0, plus the 2, that's 1, 2. And you add up, this is 4. 4 plus 3 is 7. 7 is more than 6, so 1 carry over. 4 plus 1 is 5, and then 1 plus 2 is 3, and 1 is just 1, and that's in base 6. And there we go. You see, 2, 4, 1 in base 6 times 3, 4 in base 6, you get this 1, 3, 5, 1, 4 in base 6. Okay, does that make sense? Multiplication table and do this. So why is this true? Why, to be specific, I mean, the multiplication table is true, right? Because we just add it up. It's just, you know, the essence of multiplication. But why is this method true? Why can we do this? It actually stems from the digits, the digit bundles. Okay, so maybe from a number base 10 point of view, you can see this clearer. Okay, so I'm gonna give you a number base 10 example first, and then you can see this in number base 6. Okay, so very simple. Say that you do 78. Now we are working in base number 10. Okay, the regular number base. So 78 times 23. The way we learn, we do this first, right? 3 times 8, 3 times 7, so 4, 24. There's 2 here, 3 times 7, 21, 23. And then you do 2 times 8, 2 times 7. So 16, 2 times 7 is 14, so 1, 5. So why do we need to align them in this way rather than this way, rather than this way? Why do we align them like this? Because
yeah, because we think of 78 times 23 as 78 plus times 20 plus 3. So we have to put it in the tens spot.
Exactly. Because instead of doing 78 times 23, we're actually doing 78 times 20 plus 3 here, right? So when it times 2, 78 times 2 goes from here, right? 78 times this times this 2, you get 156. But there's actually a 0. So it's actually 1560 plus 78 times 3, which is 234. So there's actually a missing 0 here. Very nice. Okay, that's yeah, exactly how it works. Yeah, and to do the digit sum here, the digit bundle here is the same. Just to show you, okay, I'm just showing you how to do this. You don't have to do this, okay? But here, if you want to do this digit bundle, you don't have to construct a multiplication table. So there were pros and cons, okay? To do this regularly, you have to construct this multiplication table. It takes a while, to be honest, right? But if you do digit bundles, you don't have to do that. I'll show you why. So here, if we do digit bundles, we have 2 times 6 squared, 4 times 6 to the power 1, 1 times 6 to the power 0, and then times 3 times 6 to the power 1 plus 4 times 6 to the power 0. Okay? So it's just a bracket times another bracket. And in the first bracket, we have 3 terms. In the second bracket, we have 2 terms, right? So you're going to open up brackets. Okay, we have to open up brackets. So we open up, we do, we first do this and this, correct? So doing these two, we get 2 times 6 squared times 3 times 6 to the power 1, right? This times this gives you this. Okay? And then plus this times this, right? So that will give us 2 times 6 squared times 4 times 6 to the power 0. Okay, and then we can wipe them out. We do the next, this and this, right? So this times this, that's 4 times 3 times 6 to the power 1 times 6 to the power 1, right? So 4 times 6 to the power 1 times 3 times 6 to the power 1 plus this times this, okay? So you keep doing this, 4 times 6 to the power 1 times 4 times 6 to the power 0, and then add and open up the last 2 brackets, okay? The last 2 terms. So this gives us 1 times 6 to the power 0 times 3 times 6 to the power 1 plus this. So 1 times 6 to the power 0 times 4 times 6 to the power 0. And there we go. Make sense? Okay, just open up brackets as usual. And always remember that you're working in number base 6. So you want to keep a bunch of 6 to the power of something, okay? If you've gone over 6, you carry over, okay? So let's do each multiplication one by one. First, The first term here is actually 6 times 6. There are a bunch of 6, right? You see? So 2 times 3 is a 6, and a 6 squared, and a 6. So that means you have 6 to the power 4, correct? 6 to the power 4. So this one is 6 to the power 4. See if that makes sense. I think it should, right? So we just do 6 to the power 4, the first one. So 6 to the power 4. Okay, and then plus second one here. This is 8 times 6 squared, right? So let's first write down 8 times 6 squared. Actually in basics, we cannot have a 8 here. You have to carry over, right? But we deal with carry over later. Okay, let's just simplify every term first, okay? Here we have 12 and 2 6s. So 12 times 6 squared, right? That's 12 times 6 squared. And then here we have 4 times 4, so 16. 16 times 6 to the power 1. Here we have 3 times 6 to the power 1. And the last one, we have 4 times 6 to the power 0. Okay? Now we're just going to deal with the numbers that are greater than 6, which are these 3 terms, right? Just these 3 terms we need to take care of. So we take care of them one by one. 6 to the power 1, so 6 to the power 4, and this 8. Now, we see this 8 as 6 plus 2, right? Because we need to carry over the 6. So we see it as 6 plus 2. The first 6 times this is a 6 cubed. And the second 2 times this is 2 times 6 squared, right? So this one becomes 6 cubed plus 2 times 6 squared. Does that make sense? Make sense, right? Okay. And then this, the second one, you do the same stuff, right? So you see this 12 as 6 plus 6. In this case, the first 6 times this, it gives you 6 cubed, right? So 6 cubed. The second 6 times that, another 6 cubed. Okay, you see, by doing this, you are sizing these numbers down, right? You're sizing these 12 and 16 and 8 down to numbers that are less than or equal to 6. Okay, and then for 16, you do the same, right? It's actually 6 plus 6, that's only 12, and plus a 4. So you plus the first 6 times 8 is 6 squared, second 6 times 8 is another 6 squared, and 4 times 6 to the power 1 is just 4 times 6 to the power 1. And everything else is the same, so you copy them, paste them down here. Okay, and eventually you wanna get like terms, right? So there's 1 6 to the power 4. How many 6 cubed? 1, 2, 3. 3 6 cubed, right? So we say we have 3 6 cubed. And then we find out 6 squared. So 2 6 squared, 3 6 squared, 4 6 squared, right? So there are 4 6 squared. And then 6 to the power 1, that's 3, 4, and 3. So 7 6 to the power 1. And lastly, we have 4 times 6 to the power 0. The first 6 to the power 4, you can see that's 1 times 6 to the power 4, right? So that means eventually our number is 1, 3, 4, 7, 4 in base 6. They're not the same. What? Why? I must have made a mistake. Let me see. 1, 3. Okay. Oh, sorry. There's a 7 here. I didn't see, right? You see? Jump to a conclusion too fast. There's a 7 here, so I have to carry over 1, right? Carry over 1 will be 1, 3, 5, 1, 3, 5, 1, 4. So that will be correct. Yeah. So there's one more thing here. There's a 7 here. You see that 6 plus 1, right? So in the end, that's 1 times 6 to the power 4, 3, 6 cubed. So this is 6 times 6, that would be a 6 squared. So that's why we carry over, right? So 5 times 6 squared, and you have 1, and you have a 4. Okay, I forgot about that 7 thing. So in the end, that's 1, 3, 5, 1, 4 in base 6. Yeah. Okay, so there were two ways of doing this. I would say both methods takes about the same time. So yeah, you can do both, anything you want. If you need to do a lot of multiplications in basics, then obviously it's very useful to construct this multiplication table. If you have a lot of calculations, right? More, at least like more than one, maybe two or three things. Okay, two or three multiplications, and then it's worthwhile to construct a table, and you can do as many multiplications as you want, right? Okay. If you only have one basic multiplication to do, then I guess maybe the second method could be easier. Could be easier. You have to distribute, right? Using all the distributive properties, and whenever you go over 6, you have to size it down. Yeah. Okay. So yeah, it really depends on you which method you want to try. Okay. So both work. Okay. So yeah, that will be multiplication. And for division, that's the same, right? Division, you're gonna do the same thing. So,
Toby, I have a question.
yeah.
Yeah, so in decimal numbers, when we divide, why do we always subtract when we get a number that like so like the number in
Okay.
yeah, why do we always subtract and then do the next number and then subtract and then do it again until we get a finite remainder?
Yeah. Okay, I got it. Okay, why? Okay, good. Very good question. Let's look at an example. Let's say we have 781, for example, divided by 5, right? For example, this, right? So your question was, why do we have a 1 here, get a 5 here, and do a subtraction, right? And we drop a number down, and we do 5, we do 25, and we do this, right?
Yeah, like
That's
in school they teach us how to do this, but they never explained why.
Yeah, because at the time when you learn about this, you wouldn't be able to understand why. That's why they didn't really explain, right? But now I believe you can explain. It's not that hard. It has the same working mechanism as that multiplication. So so try to do this. 781 divided by 5 is the same as to say times y 1/5, right? Okay. And now what you need to do is, again, to use the digit bundles. So instead of 780 or 81, write down 780 and 1. Okay. And now the first one you're going to have here is 700 divided by 5, right? So it's basically 700 divided by 5, 80 divided by 5, and 1 divided by 5. Okay. But how do we do 700 divided by 5? Now, we know that 700, we know 500 divided by 5 is 100. Okay. We are pretending that we cannot just do this, right? Because in here, you're not doing 700. Here, you're only doing 7 divided by 5, right? So we are figuring out our hundredth digit, right? So 700 divided by 5, that is, you could see the 700 as 500 plus 200, okay? So that means you have 500 divided by 5, that's 100, right? Plus 200 over 5. So divided by 5, from now on, I'm just going to write down fraction, 200 over 5, right? But don't do this, because if you want to correspond back to this, you have to do 500 divided by 5, that's the 100. And that 100 goes to here. Okay? And then you have 80 over 5 and 1 over 5, right? And now it's time to do this part, you see? This part. This part, you can add them up. That's going to be 100 plus 280 over 5. So this 280 over 5 corresponds to this part, you see? Because this 228 is actually 280 because the zeros are missing. Does that make sense? You see, the first one, that means 100. 100 times 5, the 500 is here, and that 500 corresponds to this 500. Okay? And then after that, you have this 28. This 28 is actually 280, which is this number here, 280, this number, okay? But instead of doing 280, we're actually just doing 28 divided by 5, right? So again, you have to look at this 280, instead of 280, look at it as 250 plus 3, plus 30, okay? 250 plus 30, and there's another 1 over 5 here. So that means you have 100 plus 250 divided by 5, that's the 50 part. That gives you this part, you see, 56, 50 part, okay? This 50 part times the 5, it gives you 250, this part, okay? So 250 divided by 5, that's 50 here, and you have 30 over 5 plus 1 over 5, that's 31 over 5, right? And eventually 31 over 5, you put a 6 here, that's 30. So again, you look at this 31 as 30 plus 1. 30 plus 1. So that's 100 plus 50 plus 30 divided by 5 is 6 plus 1 over 5. So that's why in the end you have 156 as a quotient and the remainder is 1. This whole process, you can also understand it as, say you have 781 candies, okay? 781 something and divided to 5 people, okay? Let's just use candies, okay? You have 781 candies and you want to divide this pile of candies to 5 people. What you can do is, and say that you're pretty terrible at division. So what can you do? You can first take out 500 candies, right? And divide to 5 people. Each person has 100 candies. Does that make sense, right? Pretend that you're really bad at division, okay? So instead of dividing 781 at one time, you can take 500 candies out of them, right? So maybe I'll write down here, 781. You take 500 candies out, you have 281 candies left, right? For this 500, you can divide to 5 people. So everyone gets 100. Everyone gets 100, right? So 5 people, each one gets 100. For this 281, you can also take out 250 and leave 31 left, okay? Leave 31 in the pile. For the 250, again, you divide it to 5 people, so each one receives 50. Right? 50, 50, each one receives 50. For the 31, you divide it into 30 and 1. And for 30 candies, you give them to 5 people, so each person gets 6. Okay, and there's 1 left over. So that means each person gets 100 first, and then gets 50 second, and gets 6 the last. So each person has 156 candies, and there's 1 remaining candy in the pile. So the remainder is 1, and the quotient is 156. Does that make sense? And that's why we do a subtraction, because basically every time, the reason why we have the 1 here is it means that every person gets 100 candies, right? Okay, this first 1 means that every person gets 100 candies. You have 5 people, so you've divided, you've taken 500 candies away from the pile and divided them. Does that make sense? You took 500 candies away, so that's why 1 and 5 are 1 and 5. And then 280, that means you're taking 2. Now you have like 280. So to be specific, it's actually 281, right? You have 281 candies here. You are taking 250 candies from it, right? 250 candies from it, and that's why each person divided by 5, you have 50 candies. Okay, and then you have 31 candies left over. You each person gets 6. Remainder is 1. Now it makes more sense. Yeah, so it's kind of hard to explain. That's why when we were small, we just try to learn the rule instead of really understanding it. Now later on, it becomes unnecessary to understand it. So that's why most people don't understand it, right? Because no one ever explained. But no one explained to me either. But you can figure this out by, if you understand number theory, you should be able to figure this out. It's not hard at all, right? Okay. Yeah, so to the division in other number bases is basically the same. You can again construct the 6, right? Construct a multiplication table for 6, or you can do the digit bundles too, okay? But usually we don't have to do divisions. Most likely we just need to tell if they are multiples or not. But we can do some divisions as an example. Let's say we do this one. Just to as an illustration. So this is 5, 3, 6 in base 7 divided by 4, right? Divided into 4 equal parts, okay? And what the result? It's asking what's the result. And 4, of course, is in base 7. So we can get the same stuff down. So 5, 3, 6 in base 7 divided by 4 in base 7. Now, it looks like we need a multiplication table, but this is pretty simple. We don't have to construct one because it takes too much time, okay? So we just do 5, 4, we get 1, right? It's 1, 0, 0 here. And that means you get 4, 0, 0 here, right? So and then you do subtraction, it's gonna be 1, 3. Do the same thing, right? 1, 3. How many 4s are there in 1, 3, base 7? Think so. You can try this. 4 times 1 is obviously 4 in base 7, right? In this case, we just need a partial multiplication table. What about 4 times 2? 4 times 2 is 4 in base 7 plus 4 in base 7. That's 8 in base 7. And every 7 you carry over, that's 1, 1, right? And obviously 1, 1 makes sense here. This is 1, 3. So we need the 1, 1. So that means we put a 2 here. 2 times 4, that's 1, 1. And we get 2 here. And we drop the 6, so 2, 6. And to figure out how many 4s are there in 2, 6, we have to keep adding, right? So let's do 4 times 3. That's going to be 1, 1 plus another 4. And that's going to be 1, 5. That's not enough, obviously. So we add another 4. You can always do this in your mind. It'll be quicker. So here we have 1, 9, carry over, so 2, 2, right? And we need a 2, 6. So obviously we just add another 4. So 4 times 5, that's 2, 2 plus another 4. And that will give you 2, 6. And yeah, that's it. So we put a 5 here. We know that 4 times 5 is 2, 6. And remainder is 0. So we divide it, you just get a 1, 2, 5 in base 7. See if that makes sense? All you need is just a multiplication table for 4 in base 7 because you're dividing by 4. If you're divided by 3, you need a 3. If you're divided by 5, you need a 5. If you're dividing by, say, 3, 4, then that's going to be really hard because that's two digit. You have to be really familiar with the multiplication in base 7, which is not possible because we won't do that many practice, right? So you really won't see that. Yeah, and this is it. Okay, so this is how to do division. We'll give it a try. Okay, so let's move on to the last part of today. So after this, the whole chapter 9 is finished. Okay, we will finish it. Determine which of the following base numbers are multiples of 6. Then basically what you need to do is just to divide it by 6, okay? You just need to divide it by 6 for any of these kind of questions. So let me give you some examples, some caveats you have to be careful. So A, you're gonna divide it by 6, right? But notice that this is only a binary digit. So you can't just divide it by 6. You have to divide it by 6 in a binary representation. Okay, so for A, you have to do 1, 1, 1, 1, 0. You can't just say divided by 6 because 6 is not a binary number, right? So you have to change it into a binary number. So 6 in binary, that's 1, 1, 0, right? So 1, 1, 0, 4 plus 2 in binary. Okay, change all the numbers in the same number base, and you can do long division. 1, 1, 1, 1, 0 divided by 1, 1, 0. Okay, that's not hard. Binary is the easiest, right? So 1, 1, 0, you have 1, 1, 1. Obviously, get a 1 here, right? Get a 1, 1, 1, 0. Do a subtraction, you have 1. And obviously, you drop the 1, 0. You get 0 and 1 here. Notice the 0. Okay, don't get 1, 1, 0. It's 1, 0, 1. Because when you drop the 1, if you only drop the 1, 1, 1, it's not enough, right? So you put a 0 here, and then drop another 1. Remember the way to do long division? Okay, so you drop the 1. It's not enough. 1, 1 doesn't have 1, 1, 0. So you're going to have a 0 here, and you drop the other 0, 1, 1, 0, and you put a 1 here, 1, 1, 0. Remainder is 0. Okay, so the answer is just 101 in base 2. So that means this number is a multiple of 6. Okay, of course, the other way to do this is always to change this into decimal representation, right? If you change it to decimal, that's very easy to see. So 11110 in base 2, that's 2 times, sorry, that's 1 times 2 to the power of 4, 1 times 2 to the power of 3 to cubed, and then 1 times 2 squared, 1 times 2 to the power of 0, and plus a 0 times 2 to the power of 0. And that will give you 16 plus 8 plus 4 plus 2 plus 0. And that is 20, 12 to 30, 30. It's just 30, right? See? And 30 is a multiple of 6, obviously. So there are 2 ways to do these kind of questions. You can always do a division, or you can do this. For your homework, I recommend you to do the first one, just to familiarize yourself with how to do long divisions in different number bases. Okay, although the second one looks easier, right? The second one is easier, but just to try to be familiar with multiplication, try to do the first one. So in question B, you have to convert 6 into number base 6, number base 4, right? And do a division. For these ones, these are easy. You just do divided by 6, okay? Yeah, time is up. So yeah, so that's all of the materials in chapter 9. After the last one, there will be review and challenge problems. Okay, so homework. I wanted you guys to finish chapter 8 challenge and do maybe chapter 9 review. Okay, there were some exercises. Yeah, maybe do the exercises first. Okay, so chapter 9 exercises, there were 9.1 to 9.5. Those are pretty easy, just a bunch of calculations, right? And then do some, yeah, chapter 8 challenge, okay?